So welcome back to our third session for today. We're going to continue with more examples. So here I was just writing down a resource use problem. Okay, let me explain what this is. So here first follow the black ink. All right, there is this intertemporal utility function. Once again, it is again a function of consumption streams. Okay. Now, in this model, consumption will be less than or equal to output. And output will be depending on some resource that we extract from the soil. Okay, you may imagine this is petroleum oil, for instance. All right, then we use petroleum oil in the production of, let's say, heat. All right, or other types of energy, and energy will give us output, and output will be transformed into consumption. All right. Now, suppose that this is a fossil fuel. All right. This resource is a fossil fuel, so it does not regenerate. So when we use it, R is extraction here. R is the amount of extraction for each T. When we use it, it will basically decrease, right? So there's a decrease directly equal to what we use of it at instant T. Okay, and of course, at the initial point, we have this given stock of this fossil fuel. Okay, so the Hamiltonian is this. Be careful. If we assume that utility is increasing, so now you should follow the red ink. So if utility is increasing, this will always bind. All right, we will always consume what we have. So what we have will be equal to consumption. So output will be equal to consumption. So our utility is this. The current value of the shadow price of the resource is this. And this is the constraint minus R, right? S dot is equal to minus R. Then we have the first of the conditions. So here I wrote it more generally, right? I take the derivative with respect to R. I take this derivative. Then there's minus Q here, so it will be less than or equal to 0. R times this derivative will be equal to 0, and R will be greater than or equal to 0. Okay, now there's once again a feasibility constraint here. So in principle, let me write it here. Actually, R cannot be greater than S, right? So this is also interesting. Maybe I should have written that way, but it is fine. I'm just showing you how to proceed. I already showed you at some point. I already showed you what would happen if you have an upper bound, right? Remember this? We already discussed that. So second thing is the constraint itself, right? The transition equation. The third thing is the co-state equation. Now be careful, our Hamiltonian does not depend on our resource stock. So this derivative is equal to 0. And finally, we have the transversality condition. Okay? Now follow the blue link. Now equation 3 directly implies that the shadow price will continue to grow. Okay? This is the path of the shadow price, because this is a linear differential equation. I can solve this linear differential equation, and for some Q0, the current price, the current value of the shadow price of this resource stock will increase. Okay, and which makes a lot of sense, right? Because we are consuming it, and there is no way we can regenerate it, so it will continue constantly grow. Now let's specify the problem even further. Once again, we assume a linear utility function, and we assume that production function where the resource use is the total amount of resources we extract is the production input. We assume a Cobb-Douglas function with alpha between 0 and 1. Okay. Then we have this result. So because of logarithm, this is separable now. Right? ln A times ln A plus alpha times ln R. So we only care about this part, okay? So the derivative, again, I'm now writing equation 1. So the derivative of the Hamiltonian with respect to R will be alpha divided by R, okay? And then I have Q here, but I realize R equals 0 would never be optimal, right? So alpha times R will be equal to Q, okay? Alpha times R will be equal to Q. So now this field, of course, alpha RT equals to QT. Now this now looks very much like the earliest example that we saw, right? Because if Q is constantly increasing, then RT must be constantly decreasing. So from this equation only and using 3, what do we have? We have RT is equal to alpha divided by QT. So RT is equal to alpha times Q0 to the minus 1 e to the minus rho t. Okay. That. So then, if I know RT at every point in time, I can write how ST change in time, right? How ST changes in time, because now I have ST dot being equal to minus alpha Q0 minus 1 e to the minus rho t. Okay? Now, what about the transversality condition? Now, realize one thing. If you multiply Qt with e to the minus rho t, right? So this thing is basically equal to Q0. Okay, and Q0 is some positive number, it goes out. So transversality condition becomes this. Okay, because the shadow price will always remain positive. This means this resource is always valuable. So the transversality condition at the end tells me that, okay, you should consume all of it when t goes to positive infinity. All right. So how do I show these in, I mean, is that true? Yes, it is true. Just look at it. Look at this equation. This part is always positive. There's minus here. So S will always decrease. But there's one problem here. How do I know exactly when t goes to positive infinity, ST will be 0? Well, the idea is this. I will show you again a graphical demonstration. So suppose that this is ST and this is, let's say, RT. Okay? Now, what I know is this. RT, if this is the optimal path, RT will be decreasing, right? RT will be alpha Q0 minus 1 e to the minus rho t. Okay? And S dot equals 0 curve, right? Basically requires RT to be equal to 0. So this is your ST dot curve. This one okay, when R is equal to 0, this is your ST dot equals 0 curve. All right? And suppose that this is your initial point. Okay, this is S0. Now, once again, what do I know? I know that R will be decreasing in time. Okay, and S will be also, sorry, I'm of course doing this entirely wrongly, right? It is not correct. This is my let's say initial stock, and R will be decreasing. When R is decreasing, remember what happens to ST. ST dot is equal to minus R, so it is minus alpha Q0 minus 1 e to the minus rho t. Okay, and the relationship between R and Q is this: alpha divided by RT is equal to QT. Okay, so alpha divided by R0 is equal to Q0. Okay, so in other words, this is actually R0. Okay, so the idea is this: in this model, there is always, again, a saddle path. And if we now be careful one thing, be careful about one thing. R is my control variable, right? And time is defined in this way. In other words, I choose how much to resource to extract at t equals 0 as well. Okay, so R0 is a part of my control system, right? It is the first value that I will choose to create this path. Because once I create this path, I know that it will be decreasing. Okay? So the idea is that if I choose a particular value, R0, this path will make me converge exactly to this point, 0, 0 point. Okay? If I choose a point lower than this, let's say I choose R hat, okay, then I will go here, for instance. Okay? If I choose a point here, let's say R tilde, I will go, let's say, here. Okay? Because this model, again, is featuring a saddle-like behavior. So, what happens here? In this point, I violate transversality, right? And at this point, I violate feasibility. Okay, here I will feasibility, here I violate transversality condition. Okay, so the choice of R at the initial point will be on the saddle path. So this is your saddle path. Okay. Otherwise, there will always be another path that will still satisfy your dynamical system, but it will not get you to the steady state. Okay, it will either violate the transversality condition or it will violate your feasibility constraint. Okay, so as you see, it is highly similar to the optimal growth problem. In the optimal growth problem, you have the initial capital stock, K0. If you choose a particular C0, so a particular Q0, right? Then you arrive at the steady state. if you choose a larger or smaller value, you violate either feasibility or transversality constraint. Okay. One thing you should be asking, or one thing that should be giving you some headache, is this: well, how can the decision maker know what variable to choose? I mean, what value to choose at the initial point? Well, that's the beauty of the full information assumption. Okay. So there is this, you know, the decision maker should linearize the model. Can linearize the model, know exactly the steady state. Now, if you take the zoom of this, so let's take a zoom. All right. So this is your, let's say, steady state. Okay. Now, this is your linearized system, right? Now you know exactly which direction. So these are all vectors, right? Exactly which direction will be the saddle path. There are numerical procedures to show that, but I will not spend so much time. Strulik have some, it is called, what was the name? It is called inverse shooting or something like that. So there's a particular algorithm. So we assume that the decision maker will know where the saddle path is, and initially he or she will jump exactly to that point. Otherwise, there is no solution, right? Otherwise, there is no solution to the problem. So transversality condition and the feasibility constraint dictates this particular value of consumption in that model. Okay. So now let me also stop here and respond to your questions if you have any. Nothing?
I don't have any question, but can we solve the first example, the consumer example?
What do you mean first example?
The skill growing example.
Oh, okay. Now I recall it. Okay, let's look at it. So the skill problem, let me share my screen. So it was something like this, right? So there's this infinite horizon again. There's consumption, there is that, and consumption will be equal to income, right? And the skill expansion will be governed by the skill investment. Okay. Now, of course, I'm dropping t's, but I can do this. Let's suppose wage is fixed, st, ht, and here, of course, st takes values between 0 and 1. All right. For simplicity, let's assume that we're going to look at for a path that is always interior. Why I'm doing that? Because otherwise the problem is not very sensible, right? If s is equal to 0, this person will not benefit from skill expansion. If s is equal to 1, this person cannot generate any income. Okay, so it is sensible to look at an interior solution in a problem like this. So this is F. We can put some constraints on utility. These are rather typical, right? We can also say something about F. We can write, for instance, let's introduce this as well. This is much more realistic. So delta H between 0 and 1, it is the skill depreciation. So for S, we can assume that this, so if there's no on-the-job training, then there's no new skills. We can, of course, assume that this is true, and we can also say there are decreasing returns. Okay. Now the Hamiltonian will be UWH1 minus S plus Q F of S delta H H. Right? And of course, H0 is given again. So this is now your Hamiltonian. Okay. So you have, so what is your control variable here? Your control variable is S, right? You choose how much to spend on the job training. So the derivative here is U prime. Then you have the derivative of this with respect to S. So it is minus WH, right? Plus you have Q times F prime S. And since it is interior, I assume that this is equal to 0. Right? Second, we have the constraint itself. So H dot will be equal to F of S minus delta H H. Okay? Then I have the co-state equation. The co-state equation is Q dot minus rho Q equals the derivative of Hamiltonian with respect to H. So it will be what? With respect to H, I have U prime again. So derivative of this with respect to H is equal to W times 1 minus S, right? I'm taking the derivative with respect to H here. So the derivative itself, then the derivative within the function. So the derivative of this with respect to H is W times 1 minus S. Then I have plus Q minus delta H. Right? Plus Q minus delta H. Yes. And finally, the transversality constraint. It is limit t goes to positive infinity, qt e to the minus rho t ht equals 0. Okay. Now, one thing, of course, you should consider. I mean, further that point. I mean, you see here utility is strictly concave, and this function is also concave, right? We just assume in that particular concavity assumption, we just imposed it. So I know that second order conditions are satisfied, but without knowing U and F, I cannot proceed very, very further, right? But what can I do is this. what I can do is this. Sorry, my grammar should be correct. So I may imagine a steady state. All right, let's imagine a steady state. Let's think about whether we can find a steady state here. Okay. Now, in such a steady state, what will happen? First of all, let me use a different color. First of all, f of s star will be equal to delta h star, right? By this equation, right? In a steady state, I will have something like this. Then, in that steady state, I will still be satisfying this equation. Okay? I will still be satisfying this equation by this. Okay? And since this is a steady state, now look at this equation here. The transversality one, transversality condition. Now h is fixed, okay? So if I write this again, so h star goes out. Inside I have qt e to the minus rho t, right? Now transversality condition dictates us that if qt is gonna grow, okay, that growth rate should be less than rho. Right? That growth rate should be less than rho if it is ever be a constant growth rate. Okay? So at the first instant, you may imagine a constant steady state Q star. Okay? And you may try to imagine finding that steady state. So if that's true, then this equation will be written in this way. With q dot equals 0, you will have something like this, minus rho q star equals minus u prime w1 minus s star minus q star, it is plus, now q star delta h. Okay, and then this equation could be again written as q star times delta h plus rho will be equal to u prime w1 minus s star. Okay, now what do you have? You have 3 equations and 3 unknowns. Right? You have 3 equations and 3 unknowns. One equation is this. Another equation is this. Now this is q star. And another equation is this. Okay? In fact, here you can separate q star as some function of S star and H star. Okay? And then you can put this back into here. Okay? Then that equation will give you a relationship between S star and H star. Okay? And then if you couple this with that, you're going to find possibly H star and S star. Okay? Then, of course, this will be satisfying the first of the conditions because Q is fixed, right? So Q goes out as well. So your transversality condition becomes this, and it is satisfied. Okay? So sometimes you can only look at this steady state because this is, this is not given in entire detail, right? If or otherwise, you can, you can now try. You go home and try a very simple version of this. For instance, utility is again logarithmic, and schooling production function is Cobb-Douglas, right? With a greater than 0 and alpha between 0 and 1. Oops. So f of s equals a times s to the alpha. So a is greater than 0, alpha is between 0 and 1. Then you can characterize the optimal path. And here, of course, we forced the co-state variable to be constant in the steady state. And it makes sense. Considering the earlier examples, a constant value in the steady state makes sense because sometimes it is always decreasing and sometimes it is jumping to a fixed value, right? I cannot tell without specifying the production function and utility function. Okay, because as you see, there's a derivative here. So the derivative of the utility function enters the picture here and here. So it will be important for governing the dynamics. Okay.
Okay.
So we have about 6 minutes. I will not start any new model, but there are some examples in your text, so you can check them. You can look at other resources as well. You can look at my website. There are problems there. Next week, I will show you a little bit more difficult problems, let's say. We can study a firm's R&D decisions. And we're going to look at a bequest problem. Okay, a bequest problem where a decision maker, a parent, will have some kids, and then at the end of his life, at the end of his or her life, he will or she will be giving some bequest to his or her children. In that model, the problem will be a finite horizon problem because life has a particular end date. Okay, so we will be considering that finite horizon problem. And then we're going to say again, there's optimal monetary policy problems, dynamic monopsony problems. So if you are into labor market issues, we can see this, we can study some models. So optimal control theory is everywhere, right? So if you are into economic theory, if you open journals in any field, you will see such problems, such dynamic trade-off, because economic life is all about dynamic trade-offs, dynamic complementarities, dynamic substitutability relationships, resource constraints. So how do we manage these resources? Technology problems, in the industrial organization problems, all in one way or another. Growth theory is basically about dynamic choices. So you will see many examples if you open any journal. In some issue, possibly there will be a new paper that studies that. So we have about 3.5 minutes, so I can answer your questions. Great. So everybody is very good at optimal control theory as well. So I am, as you see, eliminating each topic one by one. So hopefully you are spending some time and some effort to get this material right, because we will not have much time to go back and revise everything. I mean, if you want to meet with me, I can always do that. I can explain, so I have time, but it is better if you create this, working routine, so that before the class you look at new materials and you learn this stuff. It is not that difficult. So look at the paper, look at the sample exams and problems in my text, look at the models in your textbook, and 1 week after that you will have midterm. So next week we will have a class that will be our 7th class. Then in the 8th week, in week 8, you will have the midterm exam. Okay, then. I will see you next week on Wednesday, 1 p.m.
Thank you.
All right, bye-bye.
Okay, thank you.
See you.